Yes, a very good morning to all of you. Am I audible and visible to everyone over here? Yes? Okay. So how are you people doing? Preparing nicely? Studying sincerely at home or not? Sincere, huh? It should be like your dedication has to be there. Okay, good, good. You know. Okay, so how far I think we have covered in the last class? Do we remember? Shamita. Okay, beta. Fine. How far? That means resonance phenomena have completed it, right? Okay, fine. Okay, okay. So today we are, we'll start off soon. Okay. So resonance is completed and okay, fine. We can go for, I think, I have to teach you coordinate covalent bond also today, right? Okay, fine. So without any further delay, we'll start off with a, okay. Let us start off with coordinate covalent bond itself. Now, you understand this and whatever doubts you, or specific doubts you are having, we can take it in the end, not an issue. Okay, just pay attention, you'll be fine with this. Okay. Now the thing is, when it comes to coordinate covalent bond, है ना? So or else if at all I ask you what is the difference between a covalent bond and a coordinate covalent bond, many of you might have seen this arrow somewhere in the structures. Okay. So this basically represents a coordinate covalent bond. Okay. Now the thing is, if at all, suppose if I talk about a normal covalent bond between A and B. So in normal covalent bond, what we say, A is bringing its one electron, B is bringing its one electron, they are sharing and they are forming the bond, right? Because for the formation of one bond, we require two electrons. And both of them, they are bringing one electron, sharing it and making the bond. That's what is your normal covalent bond, right? Now the thing is, if at all, what if I say that both the electrons are being brought up by only one atom for the bond formation? For that covalent bond formation, only one atom is bringing both the electrons and the other one is accepting it. That means kind of a sharing, but for that sharing, only one atom is bringing both the electrons. That's how we say that it is a coordinate covalent bond. Are we getting it? Did you get a slight idea over here what I mean from this? Yes? Okay. Now the thing is, suppose if I say this is A, this is B, right? So I'm going to say that this is going to be donor atom because it is going to give. And this one, it is basically accepting it. So it is going to be the acceptor atom. Right? Now the thing is here, when it comes to donor atom, we should help others. Before, like, it should be like, if at all, this donor atom has to share the lone pair of electrons, there are certain conditions. First of all, its octet should be complete and it should have lone pair of electron, at least one lone pair of electrons. Right? See, the thing is, normally we tend to help people only when we first help ourselves, right? So we should be self-sufficient to help others. That should be the case, right? So here also, the donor atom which should be there, its octet should be complete, or donor species which is there, its octet should be complete. And atom or species I am writing here. And what is going to happen for the acceptor atom? It wants to accept, so it has to have basically the vacancy or else vacant orbital there, then only it can accept now. Otherwise you just wish to kind of want the electrons, or you just want the electrons but you don't have the space to keep it, then what is the use, right? So that's what is overlying, or else you can say the underlying principle about this. Okay, so let us try to write something about it. Okay, so can I say a coordinate bond or else a coordinate covalent bond is formed between two atoms in which one atom provides both the electrons for sharing and the other atom provides its vacant orbital. Right? That's what is how a coordinate covalent bond will be formed. Okay. So now the simplest example is, suppose I am having ammonia. Are you able to see this ammonia? You are having BF3. Right? Now the thing is, in case of boron, are you having its octet complete? It doesn't have its octet complete. It just has 6 electrons around it. So it wants to have its octet complete. Around this nitrogen, are you able to see its octet is complete? Right? Now the thing is, and it is also having a lone pair, right? So this is basically donor and this is basically acceptor. So what is going to happen? They're going to share and form the bond like this. Hai na? So suppose if I just say this ammonia plus BF3, I'll be able to write like this NH3 and you'll be having like from here lone pair to this BF3. I'll say basically this is the coordinate covalent bond which has formed here, right? And basically I'll say that this is the adduct. That means the addition of these two species has happened. That's what is adduct. Okay. Now, if the species which gives the lone pair of electron, we call this as, suppose I'm calling this as donor species. So I call this as a Lewis base because it is giving the lone pair of electrons. And this is basically called as Lewis acid because it is accepting it. Right? Now the thing is, after the formation of this bond, it's simply like a covalent bond itself, right? So I can also replace it like this. Like this I can make it. So if you calculate the formal charge, it will be minus here, it will be plus here. So did you see that I have replaced this coordinate covalent bond with this plus minus, one and the same thing? So this is the representation of it. Are we getting it? This is one of the representation of this coordinate covalent bond. Please note it down, then we'll proceed further. And here you are able to understand now for boron, what is the configuration we write down? Boron is 5, 1s2, 2s2, 2p1 we write now. If the boron is forming 5 bonds, boron is forming, 3 bonds here. So the thing is, for ground state we are writing 1s2, 2s2, 2p1. So there are only one unpaired electron. So what I do? I go for the first excited state. If I go for the first excited state, it will be like 1s2, 2s1, 2p2. So did I get basically 3 unpaired electron? You are having this 3 unpaired electron and a vacant orbital. So in that vacant orbital only it is taking up the lone pair of electrons. So the purpose of telling you this is the acceptor atom should have some vacancy to accept the electron. Are we getting it? Right? So please write this down. So nitrogen is acting as the donor atom there and boron is acting as the acceptor atom. Clear about it? Can we go proceed further? Now similarly, if at all I give you NH4 plus, right? So can we write this as ammonia plus H plus? And do you see a lone pair on ammonia, right? So it is something like this. NH3, right? Like this. H plus is there. Hydrogen just have one electron, but when I write H plus, it doesn't have any like electron there, right? So it is having vacant orbital. Nitrogen can donate there, right? Getting it? Now similarly, if at all you can easily write this as like this. Donor to acceptor plus minus. In fact, this minus would have gone. Are you able to see this? I'll be replacing. How would I be replacing this basically? Let us write down just below this. NHHH. The thing is, this bond will be replaced like this plus minus, and you are having H plus. So don't you think this plus minus will be neutralized? So I'll be simply writing like this only. Are we getting it? Similarly, if at all I am having H3O plus, so can I break this as H2O plus H plus? And here in this case also, you are having oxygen's octet complete. It is having lone pair of electron. H plus is there, which is having vacant orbital. So can I write this as, there is a coordinate covalent bond. So can I write this as this here, and here you are having positive, negative, you are having H plus here. So this will neutralize. So ultimately what do you write? You write something like this only, na? Getting it? You might have seen this structure. So there should not be any confusion. Able to understand what I'm writing here? Can we proceed further? If at all you are done understanding and writing it, okay. Now let us go for basically, suppose if I draw the structure of NO3 minus, nitrate. So in this case, do you remember we have drawn a structure like this, N double bond O, here basically O minus because there are lone pair like this, here also O minus, right? And here you had plus. So can I replace one of this plus minus, this bond with plus minus with this particular coordinate covalent bond? Can I write like that? Right? So this structure is valid, right? Are you able to see this? And this is a second period element. Yes, all of us know that. Now, let us talk about basically now SO3. For SO3, you might have drawn a structure like this. You might have drawn a structure like this, right? Sulfur can expand its octet because it belongs to third period, right? Now, I can also draw one structure. See how many electrons around sulfur? There are 6, right? Now, listen carefully what I'm saying. When you have to place the coordinate covalent bonds, right? So, you just see that you are not even violating the octet of any central element, irrespective of the fact to which particular period it belongs to. Are we getting it? Whether it belongs to, for second period, though, we can never do, right? For third period, at least they can expand their octet. But what I'm saying is, for placing the number of covalent bonds, what you have to do is, please do not violate the octet of any central atom, irrespective of the fact to whichever period it belongs to, right? Whether it belongs to third period, whether it can expand its octet or not. Are we getting it? Right? So in this case, I'm going to draw an alternate structure for this. Okay. Because in the examination, they can directly ask you in which of the following coordinate covalent bond exist, right? Now the thing is, around sulfur, we know there are 6 valence electrons. There are 3 oxygen. Now the thing is, one oxygen I can easily draw like this, double bond. There is no harm in it, right? Now for the sulfur, how many bonds made? 2 bonds made means 4 electrons gone. Now, again, I can just make 2 more bonds. That means I can share this lone pair of electrons with the oxygen, share this lone pair of electrons with this oxygen. So, how many? Basically, I have formed a coordinate covalent bond. Are you able to see that? This lone pair of electrons being shared into oxygen, right? Here also, this lone pair of electrons being shared to the oxygen, right? Now the thing is, now you tell me, after the formation of this coordinate covalent bond, how many bonds around this sulfur? There are total 4 bonds, right? 4 bonds means 8 electrons. So did you violate the octet of sulfur here? You didn't violate, right? Getting it? So that's how you will be getting the number of coordinate covalent bonds. Are we getting it? Is there any confusion here? Okay. Now the thing is, tell me this sulfur belongs to third period now. So in case, and your oxygen is capable of forming a double bond or not? We have formed one double bond. Oxygen is capable of forming double bond, right? It forms double bond. It is a divalent atom, right? Now the thing is, if you analyze these two structures, both the structures are correct, right? If at all the examiner is asking about coordinate covalent bond, please refer from this structure. If asking about number of pi bonds, you can go for this, like how many total pi bonds or how many total bonds are there, right? Now the thing is, you understand here, because there is no harm in this, because in reality, basically sulfur is able to expand its octet, right? But just for the placement of the coordinate covalent bond, we are thinking like that, right? Now the thing is, if at all the central atom belongs to third period or beyond it, and the surrounding atom is capable of forming a double bond. So what I can do is, I can replace this coordinate covalent bond with a double bond. Are you able to see? I am able to replace the coordinate covalent bond with a double bond if at all my central atom belongs to third period and the surrounding atom is such that it is capable of forming a double bond, right? But can I say the same thing here? Can I write like this? Suppose N double bonded O, and here O minus. Do you really think I can do this? What I've done, I have now tried to replace this coordinate covalent bond with a double bond. Can I do this? No, absolutely not. Because nitrogen's octet is getting violated now. And it doesn't have vacant d orbital. Getting it? So you cannot do it. So that condition you understood now. Are you able to relate to it? So I can say, suppose if I ask you, which of the following, let us say in the form of a question, which of the following is correct representation of coordinate covalent bond? Right? Between A and B, suppose. So suppose I give you A gives you B, like A arrow B. Second one is AB. You are writing plus and this. Third, you are writing A double bonded to B. But this is like A is donor atom, right? So this belongs to greater than or equal to third period. And I'm writing the condition that this is can form double bond. And I'm giving you the fourth option, which is all. Right? So it will be all like this. Are we getting it? Just now we have seen now, this particular donor atom has to belong to third period. Okay. Understood everyone? Is there any confusion? So similar way you can think even in H2SO4 also. Suppose I go for H2SO4. One structure which we all know is double bond O, here OH, here OH. Can I also replace this S double bond O by coordinate covalent bond? Are you able to see this? OH, here also a coordinate covalent bond. So in that case, the sulfur octet will not be violated and you are having coordinate covalent bond there. Clear about it? Now let us go for a few more structure. Like for example, CO I am writing. How many valence electrons are there in this? 4 plus 6, there are 10. So I am going to draw like this, a single bond. Now how many electrons used up? 2 electrons used up for the formation of a single sigma bond. So you are having 8 electrons. Now you distribute in such a way to complete the octet of the surrounding atom. Check the formal charge here, it is -1, here +1. Now the thing is, I cannot have this structure. So let us discard this structure but improvise in this structure. Are you having this? Now here formal charge is 0, 0. But the problem is that particular structure is more preferred where the octet of all the elements are complete. That is given more preference over the formal charge. So what we are having here is basically octet of this is incomplete. Octet incomplete. That is the reason we are kind of, discarding this structure. So what we can do, we can still improvise it in a better way. You can have something like this. Now if you calculate it is +1, it is -1. And this is like octet complete, this structure is acceptable. Now the thing is, I can replace like this. Are you able to see? A coordinate covalent bond. Plus 2 minus. What I've done? Plus 1 to minus 1. I've just replaced it like that. Arrow heading towards minus. Are you able to see a coordinate covalent bond exists in case of CO? Right? Now next, if at all we go for suppose N2O. So here it is like how many valence electrons? Again 10 plus 6, 16. You are having nitrogen as the central atom here. For formation of two bonds, what you've done is 4 electrons used up, 12 are there. Place these 12 electrons around the surrounding atom to complete their octet. Check the formal charge. It is minus 1. Here how much? Plus 3. Here how much? Minus 2. This is like very pathetic structure. So what we are going to do? We are not going to accept it, but we are going to improvise over it. So I am going to have something like this, a double bond here, N double bond O. So this is one of the structure. Now here it is 0 plus 1 minus 1. Can I have one more possibility of it? Yes, I can have. I can shift the lone pair here, and in response to that, I can have, like resonance is possible here, no? So I'm just drawing one more resonating structure of it. Right? So in this case, it is minus 1, here it is plus 1, here it is 0. These two are the resonating structures, right? Now the thing is, out of these two structures, this being more stable, reason being these two are like kind of, they are having same number of covalent bonds. That means pi bonds are same here, sigma framework to be anyhow do not touch in resonance. Here, how would you decide? Basically nitrogen and oxygen. Central atom charge is same in both of them. Out of nitrogen and oxygen, which is like more electronegative. Oxygen is more electronegative. So if negative charge is present on more electronegative element, that is having more stability, right? So because of that, I'll say that, okay, this is kind of more stable structure. So more contribution of it in the final main structure which we have. So in that case, what I'm going to do is, can I replace this plus minus by this, a coordinate covalent bond? Are you able to see? So it seems like N2 is giving the electron to this O minus. In fact, O, not minus, I'm saying. N2 is giving the electrons to oxygen. Clear about it? Is there any confusion? Let us talk about HNC. In case of HNC, how many valence electrons? 1 plus 5 plus 4, total 10 electrons. So you're having HNC, this framework. 2 bonds you have made. 2 bonds means 4 electrons gone. You are having 6 here. So 1, 2, 3, 4, 5, 6. You can put around carbon only. Then only its octet gets completed. Check the formal charge. 7 electrons around carbon. For the formal charge only, we are breaking it like this, right? 7 electrons around it. How many should have been in its valence shell? Only 4. So extra of 3. Here, around nitrogen, you are able to see 2 electrons. Only for the formal charge, I am saying, okay? How many should have been? 5. So there is a deficiency of 3. So this is like very bad structure. So what I can do is, I can straight away take 2 of the lone pairs and convert them into the pi bond. HN double bond C, right? So I have converted like this. I have taken both the lone pairs together because I know till the time I'm not violating the octet of this element, that's absolutely fine. Rather than going by step. So how much is the formal charge here? Minus 1, this is plus 1, this is 0. So can I also write this as HN double bond C like this, a coordinate covalent bond. Again, HCN. How many valence electrons I am having? The same, 1 plus 4 plus 5, that is 10. So HCN, if at all I am doing, 2 bonds formed means 4 electron gone, 6 remaining, 1, 2, 3, 4, 5, 6 you do. What is the formal charge? Minus 2, here it is plus 2, here it is 0. Again bring 2 electrons here, 2 pair of electrons. So you will be getting something like this, HC triple bond N, right? Now the thing is here, it is basically 0. It is here also formal charge will be 0 now. You break this and you see Formal charge is 0, here also 0. So are you able to see any +1 and -1 here? It is not there. So there is no coordinate covalent bond. Right? Hopefully it is clear to all of you. Is there any confusion here? Let me know. Is there any confusion? Is there any doubt? Let me know. Is there any specific doubt to anyone? N2O you are having doubt. See, in case of N2O, you see how we have drawn the structure. You understood this first and second structure? How we have drawn the structure? The person who has asked me about N2O, did you understand how did we draw the structure? Yes. Now the thing is, out of these two structures, I am saying this is more stable structure, more stable resonating structure. If that resonating structure which is more stable, it will have more contribution in the real structure, which is hybrid, which exists. So that is the reason I am going to place the coordinate covalent bond in this particular structure only. How? Why I am saying that out of these two, this is more stable, because see, N plus is same, right? Only thing is you are seeing here nitrogen is having negative, here oxygen is having negative. Which is more electronegative? It's the oxygen. So it should have -1. So more electronegative element having negative charge is more stable structure. So that is the reason I've just replaced this plus. This is seeming like this only, na? +1, -1. So simply I've written an arrow like this, originating from plus, ending at minus. Clear now? Yes, understood. Is there any confusion in this coordinate covalent bond further, because we are done with this? See, the thing is, at your level, they are going to ask you very, very simple thing also. Now, the thing is, if you remember ozone, which we have drawn, remember the structure of ozone yesterday, which we have done? It was like this. +1 we have placed, -1 we have placed. Now, can you tell me, will there be any coordinate covalent bond here? Can you tell me, will there be any coordinate covalent bond? Yes, correct. You are having this now. I can write like this. A coordinate covalent bond. Getting it? Fine, so now comfortable. So let us move further with the next topic now. Okay. So simple questions will only be asked. Need not worry about it. Okay. As such, I've given you, kind of typical example. So that is absolutely fine. You can do it. Okay. Now next is bond length. You can write. What is basically a bond length? If at all I have two bonded atoms, so the internuclear distance between these two bonded atoms is basically your bond length. Okay. So we can write down the internuclear distance between two bonded atoms is called as, or else is known as, bond length, right? Now we are going to see what are the factors affecting bond length, right? So the first factor being size. If the size increases, size of the atoms I'm talking about, so bond length, what happens? That increases. So suppose if I give you HF, HCl, HBr, HI. So are you able to see H is smaller, F is also smaller. Bond length will be like this. H is same, but chlorine increase, so the bond length will increase, right? So the bond length order is going to be like this. Similarly, if at all I give you F2, Cl2, Br2, I2, then again bond length order is going to be like this because of the size increasing. Then if at all I give you HH, CH, CC. So are you able to see this is involving 1s, 1s, this is involving 2p, 1s, 2p, 2p. So we see the size by the n value. N value, that means the principal quantum number. So bond length is going to be like this, right? In fact, if at all I write like this here, bond length for HH is going to be lesser than for carbon single bond, double bond, or triple bond, or else CH also, right? The thing is, for that C double bond C, every time the second principal quantum number, that means the second shell that will be involved for the overlapping, right? So, or else the subshells which are there or the orbital which are there, they'll be having that principal quantum number 2. That is the reason size more, bond length is more, right? Now, the second factor which is over here is bond order. So we know that if bond order increases, force of attraction between two atoms increases, and hence the bond length is going to decrease. So bond order is inversely proportional to bond length. So if at all I talk about bond length here, single bond, double bond, triple bond C, you know that the bond length is going to be like this, because here bond order is one bond. Here bond order is 2. Here you are having bond order as 3. Similarly, I can also write like this. Suppose I say single bond, double bond, triple bond, like that. Again, the same order because of the bond order. Getting it? Please write this, then we proceed further. And once you write, please let me know. Yes, are we done writing, everyone? Okay. Now let us see the next factor here, which is percentage S character. So if the percentage S character, if that increases, so what is happening to the orbital size? That is decreasing, and because of that we say bond length decreases, right? For example, if at all I talk about somewhere like bond length of CC, carbon-carbon bond length, and suppose if I give you, this is like sp3 hybridized. Let us say if I give you one sp3, here it is sp2, another one is like suppose sp2 sp. This is sp3, this is also sp3. Here you are having sp3 sp2, this is sp2 and sp. So where the percentage S character is increasing, here you are having 50% one and 33% one, right? So the thing is, more percentage S character, bond length is going to be smaller. Are we getting it? So this is just a comparison. Both are sp3, percentage S character is less. Here, one is sp3, another one is sp2. So slight increase in the percentage S character because of one sp2 which is there. Here, had it been the case, if I make both of them sp2, then also it will be less only, right? And the fourth factor which is there, which is delta En. That means electronegativity difference. So if delta En, if that increases, what is happening to the bond length? It is going to decrease. So if you want to write a particular order, we can also go like this. We can have, if at all, if you want, here it could be, this is sp2, sp2. Again, I can have sp2 and sp, and I can have sp and sp. Are you able to see? This is sp2 and sp combination. This is sp, sp. So as the percentage S character is increasing, the bond length is decreasing, right? Able to understand what I have written? Is there any confusion here? As the percentage S character is increasing, bond length is decreasing. So are you able to see both? This carbon-carbon bond length I am talking about. Okay. Now for this delta En, check when the nature of bond and bond order is same, then only you check this. Hai? So if at all I give you CH, NH and suppose FH. In this case, what is there? Bond order, all of them, it is one only, because I'm just talking about the single bond which is there, right? Now the thing is, nature of bond is also same because all these atoms are bonded to hydrogen only, right? So the nature of bond is also same. Now next what we know, bond length, delta En will be increasing this side, hydrogen and fluorine, maximum electronegativity difference, so bond length is going to decrease like this. Getting it? So please write this, then I'll be giving you a few questions. Compare the bond lengths in following. First one is O3, O2, H2O2. Here you have to compare oxygen-oxygen bond length. Second one, CO, CO2, CO3 minus 2, CH3OH. And let us say I give you C2H6, C2H4, C2H2. You have to compare carbon-carbon bond length. And if at all I give you fluorine-fluorine, oxygen double bonded to oxygen, N triple bonded to N. I'll solve one of the question, right? So I'll solve the second one so that you have the idea how to go about it. Simply, do we know the fact here it is C triple bond O, right? What is the bond order? Bond order is 3. See, only for that resonating structures I have given you, only from one structure if you calculate, you use the formula 1 plus number of pi upon sigma. Otherwise, simply bond order is how many number of bonds are present between the two atoms. Are we getting this very clear in our mind? Right? Here, for CO2, we'll be writing like this, na? Right? So what is the bond order here? 2. For CO3 minus 2, will I be writing a structure like this? So what is the bond order here? Resonance is possible here, na? So I can easily write 1 plus number of pi bond. Pi is 1, sigma is 2. Will I get 1.5? In case of CH3OH, I'll write this example here. In case of CH3OH, are we having something like this? I asked you to compare CO bond length here. Bond length, CO bond length you have to compare in these examples. Okay, this one. So here bond order is 1 now. And do we know bond order is inversely proportional to bond length? So can I write best will be for CH3OH. After that it will be for CO3 minus 2. After that it is for CO2 and after that it is for CO. In fact, here also you must see, is resonance phenomena possible in CO2? Is resonance phenomena possible in CO2? Is resonance phenomena possible in CO2? It is possible. Lone pair, single bond, double bond. Lone pair, single bond, double bond. You need the conjugation. Like this, it is possible. C triple bonded O. You will be having 1, 2, 3, 4, 5, 6, minus 1 like this, plus 1 like this. Resonance phenomena is possible. That is the reason it is often said that the bond length, CO bond length in this carbon dioxide, it is intermediate between a double bond and triple bond. Right? So even I could have applied the formula here like this also. Bond order is 1 plus number of pi bond here, how many? 2. Number of sigma bond also 2. So basically we will be getting 2. Are we getting this? Got it clear? In CO2 resonance is there. Lone pair. Out of 2 bonds, there is one single bond, a sigma bond. Lone pair, single bond, double bond. Do we have that framework? So resonance is possible. Did we understand it? Let me know. Yes? Okay, fine. Now please calculate for rest of them, everybody. Please find the order for others, O3, O2, like that. So be careful, like where resonance is possible or not. Conditions remain the same. Conjugation is required. sp2 hybridization of the atoms which are participating in resonance. Two questions are very simple. For second one, you tell me, did I give you CH3, CH3? Here it is CH2 double bond CH2. Here it is HC triple bond CH. Are you able to see this is sp hybridized, this is also sp hybridized, sp2, sp2. Here it is sp3 and sp3. So if at all I have asked you about carbon-carbon bond length, it is going to be like this. Did we write this as the answer for the third one? Did we write this as the answer for the third one? I'll repeat for CO3 minus 2, don't worry about it. See, in case of CO3 minus 2, can I write the structure like this, first of all? Can I write like the structure like this, right? Now the thing is, resonance is possible here, no? You are having lone pair single bond, double bond, conjugation like that. So when resonance is possible, I asked you, you can calculate the bond order as 1 plus number of pi bond in this structure is only 1. And how many sigma bonds? Achha, I have kind of written something wrong here by mistake. Yeah. How many pi bond here? 1. And how many sigma bonds? 3. So it is going to be 4 by 3. Right? So by mistake, this is my mistake here. Sorry for that. So you're having here 4 by 3. Right? Vivo, I don't require your comments here. No? Nobody is asking you forcibly to sit here and comment. No? So you can mind your own business. Are we done writing it? So if you are serious enough, then only sit in the class. Otherwise, not required. No entertainment is going on here. Serious studies, serious persons who are like serious about their career, na, those only attend the lecture. Na? That is my advice. Are we done writing it? Okay. Now, in case of this O3, O2, H2, O2, are we having something like this? Remember 1, 2, 3, 4, 5, 6 minus 1. Here it is plus 1. Now the thing is here resonance is possible. So what is the bond order? 1 plus number of pi bond is 1. Sigma bond is 2. Are we writing 1.5? In case of O2, do you draw the structure? So what is the bond order? 2. In case of H2O2, do we draw the structure like this? OO, HH. So what is the oxygen-oxygen bond order? That is 1, right? So bond order is inversely proportional to bond length. So what about bond length now? It should be like H2O2. After that, it is O3, and then it should be O2. Clear to everyone? Like this, you would be getting in the examination which bond length you have to, kind of compare. Are we absolutely fine? For the fourth one, just compare by the bond order. Higher is the bond order, lesser is the bond length. In second one, Pawan, be specific which example you want to understand. Because I've already explained for CO3 minus 2. We are just calculating the bond order there. Which specific example you didn't get, please be specific about it. Then only I can clarify your doubts, no? CO3 minus 2, just now I explained, na? Where is your attention, by the way? Huh? We are in the same class or not? The same example I just explained to someone else now. You are in online. Offline, we may understand some daydreaming might be happening. I really don't understand what is the concentration levels there. Are you playing the video game also together? Morning. Clearly, I said this is the resonating structure or this is the structure for carbonate ion. And you check resonance is possible or not. It is possible because lone pair single bond, double bond. After that, I told you that yesterday class, I have told you how to find out the bond order from one particular resonating structure itself. You need not draw all the possible resonating structures. So the formula is 1 plus number of pi bond upon the sigma bond. How many pi bond here? 1. And how many sigma bond? 3. In that case, you are having basically 1 by 3. Hopefully, you know that one of them will be sigma, another will be pi. I hope it is clear to all of you. The thing is, when certain explanation is going on, please pay attention. If this is the kind of concentration which you people have in the class, then sorry, really, it's very difficult to crack the examination. Getting it? So please pay attention when something is being delivered from this side. So bond length, we are done with that. Now let us go for counting of p pi and p pi d pi bonds. Right? Now in this case, let us understand for SO3. See, in case of what do we mean by p pi bond? First of all, you should understand that it is basically the pi bond formation which we are dealing with. And a bond will be formed between two atoms, no? Suppose if I talk about these two atoms, right? If I talk about a pi bond, right, between these two. So one of the atom is also giving its p orbital and another atom is also bringing its p orbital for the sideways overlapping for the formation of a pi bond. Then it will be p pi bond. Simply, pi bond formation between the two atoms and what these two atoms are bringing, their p orbitals. Pure p orbitals, I am saying pure p in the sense the p orbitals which have not undergone into hybridization. Getting it? Did we understand this first thing what I am trying to say? What is p pi here? Is it clear? Now, when it comes to suppose I'm having again, suppose let us say M and N. Let us say I'm changing the atoms here. Now here one of the atom is providing B, another atom is providing D for the formation of pi bond. It is possible, right? So in that case, this pi bond which is there, it will be known as p pi d pi bond. Are we getting this? Simply, one atom is providing its p orbital, another one is providing its d orbital, right? Now in case of SO3, let us try to understand this. In case of SO3, do we know this is the kind of structure which exists here? Right? So sulfur is making 6 bonds. Are you able to see total 6 bonds sulfur is making? So for making 6 bonds, sulfur should have 6 unpaired electrons or not? It should have 6 unpaired electrons. Now when I write down the valence shell electronic configuration of sulfur, do I know it is 3s2, 3p4, 1, 2, 3, 4. How many unpaired electrons I am having? Basically for sulfur I am writing in the ground state. Only 2 unpaired electrons, but I need how many? I need total 6 unpaired electrons. So what I go for? We need to go for the excitation. So first excitation state, will I be able to write 3s2, 3p3, 3d1? You're able to see this 3s2 here, 3 electrons here. In case of 3d, you are having 1 electrons. Now also there is only 4 unpaired electrons. What I want 6 unpaired electrons. So I can go for second excited state. So it will be 3s1, 3p3, 3d2. So are you able to see from S now I have sent it to D. Am I having 6 unpaired electrons now? Yes, I am having that. Now the thing is, next thing you identify what is the hybridization. It is sp2. So what will happen here after the excitation has been done? So are you able to see these 3? They'll undergo hybridization to form 3 sp2 hybrid orbitals, and I am having 1 pure p orbital in which it is having 1 electron and 2 pure d orbitals which is having unpaired electron. Did we digest fact up to this? Now, in case of oxygen, for oxygen, what do we write down? We write down 1s2, 2s2, 2p4. 1, 2, 3, 4 we are having, right? So basically only 2 unpaired electrons here. So one for sigma bond, another for pi bond. Are you able to see something like this? Na? S double bonded O. One oxygen is making one sigma bond and one pi bond, right? So what is going to happen here is you think like this. You are having sulfur. On that sulfur, are you able to see there are basically 3 sp2 hybrid orbitals? This is what we write now, sp2 hybrid orbitals. They are having one electron here. This is going to overlap with the oxygen orbital, 2p orbital, right? I'll do one thing, I'll draw it a little bit shifted here. You don't have to draw this entire thing, I'm just explaining you. Don't worry about it, okay? Plus, plus, plus. There is one electron, one electron, one electron here. Did we understand up to this? Sulfur sp2 hybrid orbitals, there will be 3 and they will be oriented in a trigonal planar fashion like this. Did we understand how I have drawn this? Okay. Now, what is going to happen is you are having oxygen. It is bringing its 2p orbital here to form a sigma bond. Getting it? Then again one more 2p which is having one unpaired electron. Are you able to see one oxygen is having 2 unpaired electron? So with one unpaired electron it is overlapping to form the sigma bond. Here also. So 3 sigma bonds done. For 3 oxygens, this is for oxygen. Getting it? This is for oxygen. Oxygen, 2p orbital. Now the thing is, these p orbitals, they will be perpendicular to each other. We are just talking about the hybridization of the atomic orbitals of the central atom, not the surrounding atoms. Now the thing here, are you having oxygen orbital like this, one 2p orbital, and do you have like one pure p orbital from sulfur? They will be overlapping sideways to form the pi bond. So that is basically one of the pi bond is p pi p pi. Right? You think like this, sulfur is sp2 hybridized, no? So if it is sp2 hybridized, there are total 3 p orbitals. 2 have participated in hybridization. So there is only one p orbital which is remaining, which has not participated in hybridization. And that p orbital only from the sulfur, and oxygen will always be able to only provide p orbital because it doesn't have d orbital. So you are able to get this p pi bond. Is this clear to you? Is this clear? Right? Are you able to understand the overlapping here? You are having this p and this p, right? This p orbital and this pen, you are able to see black one, right? Sideways overlapping. Now the thing is, second one is what? With the S sulfur, you are having pure d orbitals available, right? P2 is got consumed, involved. Now you are having 1d and you are having p here. So you will be having sideways overlapping. So the other bond is going to be p pi d pi. Similarly, d from here, p from here, you are going to have p pi d pi. Getting it? So simply, if at all you are being provided, you don't have to do the overall analysis. That is only for your understanding. I have told you everything here. Now you just see how do you predict. You simply find out what is the hybridization of the central atom. Here in this case it is sp2. So for sp2 there is one pure p orbital is there. And oxygen by default it is always going to provide only p orbital because it doesn't have d orbital for the pi bond formation. So one p orbital is left now. So can I say one of the bond, it is one p pi, or else you need not write one here. Are you having this as p pi bond? I could have written any one bond as p pi. It's like randomly I have taken for this. Are you able to understand? Now the other one is definitely p pi, p orbital from oxygen and d orbital from sulfur, because it doesn't have now p, because it got overlapped with the another oxygen, and another one will be also p pi d pi. Getting it? So at present what you do, you just write down this as first. Hopefully everybody has written the heading. If at all somebody is interested in writing the explanation, later on you can write it. Okay. But at present for your level, if you just need to find out the p pi d pi bond, right? So this is the way you can go for. I'll give you few more examples to do in the class, and you can verify whether you are going it correct, like whether you are doing it correctly or not. Is that absolutely fine with all of you? So please write this and then we'll proceed further. Just write this portion, that is sufficient. Then I'm going to give you few more examples. And do remember, if at all the double bond is between two such atoms which belong to second period. So do you think there is any scope of d orbital there? It's by default going to be p pi bond. If at all the double bond is between those two atoms which belong to second period, then there is no scope of d orbital. So it is going to always have p pi bond only. Okay, hopefully everybody has just written it. So I'll write down few more examples and you do it, then we'll check the answer. CO3 minus 2. For your help, I'm drawing the structure also. Here lone pairs I'm not drawing, but it is understandable lone pair is there, right? Or else draw it, otherwise later on you'll say, ma'am, you didn't draw in the structure, so better I don't give you that scope. SO4 minus 2, S double bond O, O minus. NO3 minus N double bond O. You can also go for H2S2O8, which is Marshall's acid. In this case, you can have S double bonded O, double bonded O, OO, S double bond O, double bond O, OH, OH. Find out the number of p pi, d pi, or else p pi bonds here. I've given you the structure. As such, in the examination, maybe structure will not be given, but you know how to draw them. Multi-centered, you don't worry about, you will eventually learn. Yes, are we done? Can I discuss it? You just have to count. First, find out the hybridization of the central atom, then you can identify. In this case, hybridization is sp2, and moreover, these two are what? Second period element only, so there is no other scope. P pi bond only. For the sulfur, sp3. So what you are having? For the sulfur, all the p orbitals, they are gone. They have already participated in this particular hybridization. So what is left out with? Only D. And oxygen is providing P only, so P pi D pi. In fact, both of them is P pi D pi. Here hybridization, we know it is sp2. This is going to be P pi only. Both are second period element. There is no scope of D orbital there. Here it is sp3. Here also it is sp3. So basically both of them, and here also both of them, they are going to be P pi D pi bonds. Oxygen is providing P orbital. For sulfur it is D. So total 4 P pi D pi bonds here. Are we clear about it? Yes? Okay, so we are done with that. Now let us proceed further, which is dipole moment. Now remember, when we were learning about the Fazan's rule, I told you that basically any ionic compound, it's not 100% ionic. There will be certain amount of covalent character associated with it. Similarly, here basically if at all I say I've got a covalent compound, there will be to some extent some amount of ionic character associated, right? So to explain how much amount of ionic character is associated with a covalent compound, basically this concept was thought of, right? Now the thing is, if at all I look for this HCl, right? Do we know that the electron, this is a covalent molecule or not? H and Cl, both are non-metals. The bond between them is covalent bond. Now, do we know the fact that electronegativity of chlorine is greater than hydrogen? So whatever is the electron density here, it is not equally shared. This will be slightly more attracted towards the more electronegative element like this. Slightly more attracted. I didn't say that the electrons are leaving their original atomic orbital. I'm not writing completely as H plus and Cl minus. I'm just writing the partial charges because those electrons here, they are being slightly more attracted towards chlorine. Right? Now, are you able to see two poles generated, positive, negative? Have you ever identified a battery? There it will be like positive, negative terminals will be there, na? Like two poles, dipoles. So here, two poles means dipoles, right? So are you able to see a dipole generated here, right? So dipole is there, polarity is there in the molecule, in this particular covalent molecule, right? Now the thing is, there is a particular direction. What is the magnitude, or is, kind of, what is the extent to which polarity is there? We show it by this dipole moment. It will be originating from this plus to minus. That means from less electronegative to more electronegative. So basically, what do we understand by this dipole moment? First of all, it is having a particular direction. That means it is a vector quantity. And what do we know? Other thing, that basically it is going to account for the polarity which is present in a particular bond. Are we getting this? Right? So we'll write down one statement here. It is a vector quantity. It means it is dipole moment we are talking about. It accounts for polarity of bonds, right? And how do we write down mu? Mu is given by Q into D. This Q is basically the charge, electronic charge which will be there. D is either the bond length or else distance between the two atoms. Now the thing is, what is the SI unit? SI unit of mu? Coulomb into meter. This is coulomb. And what is the CGS unit? CGS unit of mu is basically ESU, electrostatic units. Electrostatic, ESU, centimeter. And the most commonly used unit, it is basically DIVYA. Based on the name of the scientist who gave this concept, most commonly used. Normally we have a misconception that basically DIVYA is itself the SI unit, no? Right? Now, 1 DIVYA is 10 raised to power of minus 18 ESU centimeter, or else it is 3.33 into 10 raised to power of minus 30 coulomb into meter. So simply we need to remember this relation. Could be asked. Please write this and then we'll proceed further. Written? Okay. Now the most important concept which is asked from this particular simple topic is whether a molecule is going to be polar, non-polar, whether it is having a permanent dipole moment. So for that we are going to make a particular flow chart and make sure that you are making this flow chart along with me, and then we'll understand the application part of it. As such, it is very simple. Do not worry about it, right? So broadly, what I'm doing is classifying these molecules into two. One is diatomic, another one is polyatomic. Now, in case of diatomic also, I can have two categories. One is homonuclear, another one is heteronuclear. When I say homonuclear diatomic means what? Diatomic means two atoms. Homonuclear means I am having two same atoms, right? So the thing is, what I am having is suppose H2, Cl2, F2, O2, right? Now the thing is, etc. Do we have here any electronegativity difference? No. So will there be any polarity in the bond? No. So the thing is here, I am saying that they are going to be non-polar always. Right? So I'll be saying their mu is 0. Heteronuclear, that means two atoms, but they will be different. So definitely they are always going to be polar. Reason being, there will be electron negativity difference always existing between them. So if at all I write CO, NO, CN, etc., or else let us say HF. So here I'll say that delta En is always not equal to 0. So they're going to be polar always. There is no doubt about it. Hai? So their mu is not equal to 0. Getting it? In case of polyatomic, basically we know now that this particular dipole moment is a vector quantity. So for polyatomic, we need to identify the net dipole moment which exists in that particular molecule. Net dipole moment. Hai? So we need to look about the vector sum. Hai? Do not worry, we don't have to apply mathematics here. I'm just telling you. So we need to see whether it is symmetrical molecule or whether it is unsymmetrical. Unsymmetrical. So if it is symmetrical, I'm going to have net dipole moment as 0. The vector summation of all those. So net dipole moment is going to be 0. In that case, it is going to be non-polar if there is any kind of symmetry there. Here, I'll say that net dipole moment is not equal to 0. So in this case, it is going to be polar. Please write this so that we can understand how are we applying this. Okay, hopefully everybody has written. Now let us see a few examples here. Suppose if I write, let us say I'm giving you BCl2, right? So the thing is, I'll be writing the structure like this, and for this dipole moment, you bring back your VSCPR table in your mind. That will really help you out, okay? So two things to arrange. This is the only regular geometry which I am having. Are you able to see the dipole moment will be directed like this? And what I'm going to have, mu net is equal to 0 or not? So this is going to be non-polar. Did we understand? So the molecule has polar bond in it. But the way dipole moment is basically oriented, it is going to have 0 dipole moment. That means net dipole moment is 0. Okay. Second one, suppose if I write CO2, are you able to see that I'll be drawing the structure like this? So are you able to see the polar bond is there? Polar bond in the sense this is more electronegative. I'll be able to write down delta minus, delta plus like that. Polarity is there. But overall, the molecule is non-polar. Why it is non-polar? Because of the placement or else orientation of these two dipole moments. So mu net is 0 here. It is going to be non-polar. Let us talk about CO. Do I need to even draw the structure of it? Do I need to draw the structure of it? No. I know it is heteronuclear diatomic. There is electronegativity difference. So this is going to be polar. Right? Let us see another example. Like suppose BF3 I write, SO2 I write, CH4 I am writing, NH3, NF3. So here just recall, you are having three things to arrange. All of them they are atoms, that too same atoms. Regular geometry is there. So do we know that the dipole moment, they will all be at 120 degree with respect to each other and they are going to cancel out each other. Resultant of these two will be somewhere and it is going to cancel out this, right? So basically because of that dipole moment vector summation itself, we are saying three vectors placed at 120 degree, they'll cancel out each other. So mu net is equal to 0. It is going to be non-polar. Simply what you have to see is there is a regular geometry now, BF3. There is no lone pair on the central atom. All the surrounding atoms are also same. It is trigonal planar regular geometry. So definitely you will have basically non-polar, right? Again, for SO2, I have three things to arrange, but are those three things same? They are not same. I am having two oxygen atom, one lone pair. So it is not a regular geometry. Not a regular geometry in the sense it is going to be polar. Reason being the dipole moment for lone pair will be always directed away from the nucleus. For this oxygen, out of sulfur oxygen, oxygen is more electronegative. So there will be like for both of them, there will be certain net resultant of these two bond pair. And always remember the dipole moment because of the bond pair, it is not always going to be equal to the lone pair, right? So there has to be like after cancellation also there will be certain dipole moment existing. Are we getting it? Now in case of CH4, what we are having? A regular geometry, all the surrounding atoms same, there is no lone pair, it is going to be non-polar. Mu net is 0. NH3, and NF3. Basically again four things to arrange, but all those four things are not atoms. You are having one lone pair also. Irregular geometry. So again, what is going to happen? Mu net is not equal to 0. It is going to be polar. So are we able to see here dipole moment like this? Here the direction will be little bit like this. There will be certain cancellation. So mu net here is also not equal to 0. This is also polar. But if at all I ask you to compare between NH3 and NF3, whose dipole moment is more? NH3 or else NF3? Whose dipole moment is more? NH3 or NF3? Whose dipole moment is more? It is NH3. Because here the net resultant dipole moment of these three will be getting added up with the dipole moment of this particular lone pair of electrons. Here there will be direction is opposite. The net dipole moment of these three NF bonds, that is pointing in different direction and you are having dipole moment because of the lone pair up. Getting it? So because of that reason only ammonia dipole moment is more. And people tend to go for just the electronegativity. Okay, I'm writing few more molecules. You tell me dipole, whether it is polar or non-polar. Did we understand up to this? Whatever examples I have taken, is there any confusion? Understood, no? So will you be able to answer few questions, right? Okay, let us see. If at all, I think which example I was talking about? I was talking about 8th example. Suppose if I take PCl5, I take SF4. Now, are you able to see that you have to arrange 5 things around this central atom? Is it a regular geometry or not? It's regular geometry, na? TBP, surrounding atom same, everything same. So are you having mu net equal to 0? It is non-polar. Just break this into 2. That means you just take these 3 in a plane. So like BF3, you take it. Then one above and one below, they are going to cancel out each other. Right? So it is going to be non-polar. Clear? What about SF4? In case of SF4, I am having something like this. 5 things to arrange, but out of that one is lone pair. It is not a regular geometry. So it is going to be polar. Mu net is not equal to 0. Getting it? Now, let us say I am giving you XEF2. So for XEF2, do we know this is fluorine? Here one lone pair. Here you are having one lone pair like this. Comment about XEF2. Is it polar, non-polar? It's non-polar. Very good. It's non-polar. Mu net is 0. Getting it? These three which are there, lone pair dipole moments, they will be directed at 120 degree with respect to each other. They are going to cancel out each other. And these two axial, they are going to cancel out each other. Got it? If at all, I give you for IF7. Fluorine here, 5 fluorine in this pentagonal planar, one above, one below. First of all, tell me, is it a regular geometry or not? IF7. It is a regular geometry, na? 7 things to be arranged around the central atom. All those are same atoms, pentagonal bipyramidal. You just have to see that. Mu net is 0, non-polar. Next, XEF5 minus. So basically you are having like this, xenon here, 5 fluorines here, pentagonal planar. You are having one lone pair above, one lone pair below. Comment about this. It is again non-polar. Reason being 5, pentagonal planar is there now. So all those dipole moments at 72 degree, because if they are at equatorial, dipole moments will be aligned at 72 degree, they are going to cancel out each other. Right? Good. Next, if at all I ask you about XeO3F2, its structure is like this. Is it going to be polar or non-polar? Is it going to be polar or non-polar? Non-polar. Very good. Right? Because mu net is 0. Tell me about water. Last example, I am taking this. 4 things to arrange. All of them, they are not atoms. It is going to be polar. Good. So it is going to be polar. Mu net is not equal to 0. You are able to see lone pair like this, directed like this. And here, like this. Getting it? So there are a few more orders which are remaining, right? So hopefully you are clear about it. Okay, so please revise the theory properly and you write down all those things in your notes properly and just read it very sincerely. Be attentive in the lecture. So that's what is required. Okay, so see you in the next lecture and wish you all the best for the test.